This is 7.1.5. Here we discuss least square solution, a summary. The least square solution is only applicable for A of this size when number of rows is greater than the number of columns. This is because only in this case the vector B sometimes is not in the column space of A matrix, and when that happens, then we have to find the least square solutions. What about the other two cases? When A is a square matrix or A is a short and fat matrix. For case A, when A is a square matrix, m rows equals to n column. Additional to that, if all the columns or the rows are independent, then A is invertible. In addition, B would be of dimension m as well. And since A is full rank, then B will definitely live in the space of A, and therefore we can solve explicitly AX equals to B by multiplying A inverse of AX equals to A inverse of B. This cancels to be an identity matrix, then we are left with AX equals to A inverse B. Using these solutions, we would precisely get AX equals to B, a unique solution, and there is no error in approximation. What about the second case? In the second case, A is a short and fat matrix. In this case, the number of equations is the less than the number of features or columns. The vector B is also of dimension Rm, is also a short vector. In this short and fat case, typically we have enough columns of independent vectors for columns of A. In this case, B can be constructed by many different types of columns of A, that is, it has infinitely many solutions. Hence, the problem is not a least square problem. Instead, it is to find which combinations of A such that the norm of X, the coefficients in AX equals to B, is minimized. This typically is not our problems to solve. Instead, our problem to solve is case 3, the least squares solution, where B is not in the column space of A. In the last few slides and lectures, we have discussed how to find the best X using the normal equation. We showed that X hat is equals to A transpose A inverse A transpose B to solve for the least squares solution. This approach is called inverting the normal equation to solve for X hat. Later on in chapter 8, when we perform SVD, we will solve for X in another way. X hat is equals to A pseudo inverse multiplied by B. MATLAB has the function P inverse, for P stands for pseudo inverse of A. Lastly, we have mentioned that we also can solve for X using the Qr factorization. The details is in the next slide. Let's go through it briefly. Given AX equals to B, and A can be factorized in Qr, where Q is the octonormal matrix, that is, Q transpose Q is equals to I. and R is an upper triangle matrix. Basically, it looks like this, with elements on the diagonal as well as above the diagonal. And along the diagonal, it has non-zero elements. What this is asking for is that A is invertible or non-singular. Now, when A can be decomposed as QR, we simply replace A as QR, writing AX equals to B as QRX equals to B. Multiplying both sides on the left by Q transpose, we have Q transpose QRX Q transpose B. Remember that Q is an orthonormal matrix. Q transpose Q equals to identity, reducing to our last equation, Rx equals to Q transpose B. Once we have reached this point, since R is an upper triangle matrix, we can solve for X simply by back substitution, or of course if we are lazy, we use this, as in we perform R minus 1 times Rx equals to R minus 1 Q transpose times B. R minus 1R will result in identity because the upper triangle matrix is non-zero in the diagonal elements we are assuming, and therefore it's invertible. However, we'll never do this in practice because there is no much point to perform R minus 1 if we can perform A minus 1 directly. For discussion, please take a look at Dr. Payam's link where he used why use QR to solve for AX equals to B, and the reason is that it is computationally efficient, where he talked about the number of multiplications required for these operations. So in summary, we see that there are actually three ways, at least we now know, to solve for the to solve for the least squares of AX equals to B. Thank you.